Distinguished guests, colleagues and friends, it's with great pleasure that I welcome you to the School of Physics and Astronomy for the presentation of the 2016 Robert Street Doctoral Prize in Physics. The prize, of course, is named in honour of Professor Robert Street, AO, who passed away on the 4th of July 2013. In fact, this year marks the 5th occasion in which the prize has been awarded. Once again, I'm pleased to welcome Robert's daughter, Professor Allison Street, AO, and her partner, John Barkler. In a little while, I'll ask Allison to make the presentation of the award to the 2016 recipient, Dr Freda Werdiger. We're also video recording today's presentation so that Allison and the Street family will have a record of it. Of course, I'd like to very warmly welcome Freda and her family to this award presentation. We're delighted to have you here. The Doctoral Prize in Physics is made possible through the generous bequest to the school by the late Professor Robert Street and his late wife Joan. From the outset, I'd like to thank the Street family for their incredible generosity. Thank you, Allison. So the occasion will proceed as follows. First, I want to provide some background on the late Professor Robert Street. I'll then read out the nomination for Dr Freda Werdiger and then ask Allison to say a few words and to present the award to Freda. Then Freda will be invited to make a short presentation on the work that led to the award of the prize. When I said a short presentation, Freda said, "We'll see." So I'm not sure, but I will not intervene. Following the presentation and some photographs, the refreshments will be served at the back of the seminar room. Professor Robert Street, Bachelor of Science, Masters of Science, PhD, Doctor of Science, honorary doctorates, Fellow of the Australian Academy of Sciences, Fellow of the Australian Institute of Physics, Officer of the Order of Australia. Robert Street was born on the 16th of December 1920 in Wakefield in Yorkshire, United Kingdom. In 1941, he received a Bachelor of Science from the University of London, actually undertaking a degree at Bristol because at that time London was being bombed. He began his career during World War II working at the Air Defence Research and Development Establishment, conducting work on the absolute measurement of power. In 1944 and 1948, respectively, he received a Master of Science in the relatively new area of wave mechanics and a PhD on absolute measurement of power. At the end of the war, Professor Street was appointed as an assistant professor in physics at the University of Nottingham. In 1954, he became a senior lecturer at Sheffield. And of course, in 1960, Professor Street moved to Australia to become the Foundation Professor of Physics at Monash University. In 1966, he earned a Doctor of Science from the University of London. In 1973, he was elected to the Australian Academy of Sciences. In 1974, he was appointed as the Director of the Research School of Physical Sciences at the Australian National University. From 1978 until his retirement, I use the word retirement because many of you have been at previous occasions when I went into the detail. During Robert's retirement, he published 119 papers, got ARC grants, and had more citations than many of us would dream of. But in any case, from 1978 until his retirement in 1986, Robert Street was Vice-Chancellor of the University of Western Australia. He told me, and it's recorded in his memoirs, that even as Vice-Chancellor, he would be the first to receive the copies of Physical Review letters, which he would read before passing on to his colleagues. Robert received many awards, including honorary Doctors of Science, fellowships of the Australian Academy of Science, the Australian Institute of Physics. In 1985, he was made an Officer of the Order of Australia in recognition of his enormous contributions to Australian education and research. Whilst we talk today about e-education and the kinds of outreach activities that we're all told to do, back as early as the early 1960s, Robert was presenting things on the Australian Broadcasting Commission. In those days, you could actually stand up with a straight face and get away with talking physics on the ABC. In 2011, we were fortunate to have Robert join us for the 50th anniversary of teaching research in physics at Monash. We took Robert on a tour of the Australian synchrotron, and it was remarkable to observe how many interesting and probing questions he asked the young scientist who was showing him the beam lines. It was clear how much he relished being in an experimental facility and interacting with the next, or perhaps more accurately, the next generation of scientists. To quote from Robert, someone has said that this life in science is rather a childlike existence. I think it is, and as soon as you lose the idea of wonder at very simple things happening to you, you may as well go and be a grumpy old man somewhere else. So this very short overview of a stellar career of Professor Robert Street, who affectionately was always known as Bob to staff and students, it does not do justice to a remarkable man and his career. Bob was an inspiration to us at Monash in the 1960s and 70s. I hope this award named in his honour will be an inspiration to future generations of physicists at Monash. I'd now like to say a few words about Professor Allison Street. It's of course my pleasure, as always, to welcome Robert's daughter to make the award. Professor Allison Street was the head of hemostasis and thrombosis at the Alfred Hospital and Vice President Medical of the World Federation of Haemophilia. She has been actively involved in haemophilia on the international stage, being made an officer of the Order of Australia in 2005 for services to medicine. She is a chief examiner for the College of Pathologists and actively involved in the College of Physicians. I'll shortly ask Allison to make the award of the 2016 Robert Street Doctoral Prize to our awardee, Dr Freda Werdiger. However, before doing so, let me just say a few words about Freda's work. Freda joined the School of Physics in 2006 as an undergraduate and completed her honours degree in physics in 2010. She then proceeded to pursue a PhD in theoretical physics under the supervision of Professor David Paganin and Dr Marcus Kitchen. Research carried out during Freda's PhD led to 3 first-authored papers, including 2 in the high impact factor journal Optics Express. Notably, she won the Faculty of Science 3-minute thesis competition in 2015. Freda, note, it was the 3-minute thesis competition. Freda was awarded the degree of Doctor of Philosophy in 2016 for a thesis titled Argand Plane Mappings. Her research provides a comprehensive mathematical study of optical and X-ray wave fields. But remarkably, she complemented her theoretical insights with experiments conducted both at Monash and the Springate synchrotron in Japan. Her work has applications beyond electromagnetic fields to more general fields, including spinors and multidimensional coherence functions. Dr Werdiger is currently working as a postdoctoral researcher in the Department of Mechanical and Aerospace Engineering at Monash, where she's also the manager of the Laboratory for Dynamical Imaging, again showing that a degree in physics has got wider applicability. It is therefore my great pleasure to ask Allison to present the 2016 Robert Street Doctoral Prize in Physics to Dr Freda Werdiger. Could you please come forward?
Thank you very much indeed, Michael. It's always a great pleasure for John and I to come out here and get our 10-minute update on what's going on in physics, because we certainly missed the input that we had from Dad, and you've taken that over beautifully. Thank you very much indeed. Freda, it's absolutely wonderful what you have achieved and what you're doing now. I really congratulate you, and I know that my father would be very proud to see such a competent and pleasant young lady getting this award. So to your very proud family as well, congratulations on the production of Freda and Freda's production of all of your results. And I'd like to award you this. It's the Robert Street Doctoral Prize in Physics, awarded annually to the candidate who produces the best PhD thesis based on work carried out in the School of Physics and Astronomy at Monash University, 2016, Dr Freda Werdiger. Thank you very much indeed.
Thank you, Allison Street, Michael Morgan, and the School of Physics and Astronomy for the enormous privilege of receiving this award. I especially want to thank my family for being here and for their continued support of me, for which I am truly grateful. I am also particularly excited that my grandmother is here, because now I get to live out the idiom, which I know that I really understand something if I can explain it to my grandmother, which is a little insulting in general against grandmothers, but anyway, it's an idiom. I will talk you through some of the research, or some aspects of the research that's won me the prize. And after that, I'll ask for just a few more minutes of your time so I can use this platform to thank some people. My thesis was entitled Argand Plane Mappings Induced by Complex scalar wave fields, and it was in essence a study of fields. So what is field theory, or what is a field? A field is just a transmission across some intervening space. It's a space where an action is continuously occurring. A field theory will define a mathematical equation or an expression for every point in that space. And that expression will determine how a body within that field will behave. A good example is a magnetic field. You have a magnet that produces a field around it. And we have a mathematical function that will determine what happens when you put a second magnet in that field. You've just focused on me because the slides aren't going to be that helpful. My thesis focuses largely on optical fields, so the transmission of light from a source. Sometimes visible light from a laser, and sometimes X-rays coming from a synchrotron. And it's to study how that light behaves upon making contact with objects, or simply just via propagation through space. We look at light in terms of what we can measure about it. So its intensity, how bright it is, and the direction that that light travels, which is called the phase. These are the quantities you can actually measure in light. They're measurable quantities, but you can't really do anything with that information in terms of making predictions without the use of mathematics. So what we do is we plug those measurable quantities into a mathematical equation, which we call the complex function. And the symbol behind me just represents the complex function. It's complex in the sense that it has a real and imaginary part to it, but if you don't understand what that means, it doesn't really matter, because the point is this is just a trick that we use. We plug those quantities into this function, so we can do tricks with it. We can answer questions like how does those quantities change over time or over space, or upon becoming in contact with something like a bone. So we have a complex wave function that defines X-rays, and we use that to answer the questions of what happens when the X-rays comes in contact with a bone. So it's just a bookkeeping trick. It's just a trick that we use so we can actually predict change. So what have I actually done in my thesis? I've floated the idea that you can visualize the complex function in an entirely different way to get information about the physicality of the light field. While it is intuitive and reasonable to evaluate the wave function over physical XY space, that is, when I'm walking across the physical space that the light is actually happening and I'm evaluating the light as I go, that's a very reasonable thing. It's actually quite difficult to visualize things from that perspective, because you have to look at the quantities separately. You look at the intensity as I walk across XY space, then you look at the phase as you walk across XY space. So you don't actually get a nice visual picture of the dynamics of that field. You can't directly visualize a complex function because it has imaginary numbers in it. You have to separate it into its measurable quantities. So instead of seeing how the complex function changes over XY space, I visualize it in the Argand plane, which is this thing. Ignoring all the symbols, this is the complex function that exists in XY space. I mapped it to the Argand plane, so instead of plotting it over physical space, I plot it against its real and imaginary numbers. But actually, what I did really is plotting the phase against the intensity. So instead of looking at the phase and then the intensity, I'm looking at how they actually interact with one another, which is a completely new perspective. And I wanted to see what kind of information I could find doing that. So what I did was I started with a random noise, really, and produced something called speckle. This is an image of the speckle that I produced. And I just took a tiny window up. You can see how complicated that is. This is the intensity of the speckle field, and this is the phase of exactly the same speckle field. And just a small aspect, you see how much information there is and how complicated it is. Also, I want to point out these sort of sharp features over here are called vortices. They're really interesting features that have a lot of study around them. And the field is completely littered with them, so they're everywhere. So I took that intensity and that phase, and I mapped it to the Argand plane, and this is what I saw. So it's more structured than that, obviously. It's not so random and fuzzy. It's highly structured, but it's obviously very complicated. And I also noticed these features here, different sort of little points and different features which actually evoke very much the physicality of what you see at the bottom of a swimming pool. So I refer to them as caustics, even though I was told off by Michael Berry directly, because while caustics are actually physical, these aren't existing in physical space, they're abstract. So there is a proper term that I use, but colloquially I can refer to them as caustics. And he actually said to me, I challenge you to find the physical meaning of these caustics, Freda. Challenge accepted. So there's a lot of information there that's possessing, but it's very difficult to look at and it's very complicated. This is a diagram. Oh, actually, these lines over here, I sort of got rid of everything that wasn't a caustic, so I could highlight just those caustic features and trace out sort of where those were occurring, just to sort of get a better sense. But it's so complicated. And I also did things like this, like I thought, okay, well, if I increase the size and decrease the size of the speckle and have more vortices and less vortices, I can kind of see how the arcane plane changes, how it seems to become more complicated the more vortices there are. Okay, but without really knowing what I was looking at, it was very difficult to actually make sense of this and find out what is the meaning behind it. So I went really back to the basics. I asked the questions. What is the simplest exemplar of this problem? So I thought about the most simple object that I could think of, which was a straight edge. And I mapped that. That's the straight edge. The simplest thing I could think of. Okay, let's just see. I'm going to take away this speckle field with the vortices, which is complicated, and I don't understand it. And I'm going to send some light at an edge and see what happens. I mapped that to the arcane plane and got this spiral, which is actually a very well-known object, which is very helpful. It's called the Cornu Spiral, and it's well-known. So it was a good platform to start from. Notice as well that it's actually just a one-dimensional trace. It exists in 2 dimensions, but it's just a 1D trace. It's a very far cry from these like beautiful, complicated objects. So of course begs the question, what makes that turn into this? So I tried to increase the complexity of the object. I tried a cylinder. I thought, okay, 2-dimensional object. Chucked X-rays at a cylinder, got this. It's much more interesting, but it still is a 1-dimensional trace. There's no caustics here. So I thought about how the cylinder and the edge are actually intrinsically 1-dimensional objects. If this is a straight line, I walk across the straight line, nothing is changing in those directions. It's literally just one line. The same thing as with the cylinder. This is a cylinder. It's not changing in this direction. It's only changing as you walk across and in one direction. It's just the thickness. There's nothing happening up there. So it really just produces just a trace again and again. So I thought about a sphere. A sphere varies in 2 directions, but it's symmetrical. So it's really just repeating the same thing over and over again. So what I decided to do, I realized I had to break the symmetry that was intrinsically possessed in those objects. Yeah, so I put a sphere inside a cylinder. So the symmetry of the sphere is solved by the fact that it's lying against the varying background of the cylinder. The thickness of the cylinder is changing as you walk across the sphere. That means the amount of light that transmits through the cylinder is changing because the thickness is changing. So I was able to break the symmetry that those subjects seem to hold, and voila, caustics. And because of the way I meticulously built up the complexity of the problem, I was able to look at the arcane plane mapping and understand exactly what it is that I was looking at. This is the particular signal that's given off when you have a sphere embedded in a cylinder. The breaking of that symmetry caused those spiral traces, and you can see the outline of the spiral trace, to sort of smear out because of the varying background. I actually call it the Cornu schmear, but the person that reviewed my paper didn't like that term, so it stayed out of it. But it is, in essence, it's just smeared across because the symmetry is broken. So when I look at this particular signal that happens when you put a sphere embedded in a cylinder, I think about things like the future of drug delivery, because perhaps in the future, drugs will be delivered to a targeting point, maybe in some sort of bubble form, and when it reaches the point, you can use some sort of ultrasound device to locate them and give off a signal that will release the drugs at that point, it makes me think of the applications of having an excellent understanding of the signal that's given off by that object. And because I'm sort of ramping up the complexity of the object, that's how you build to a generalization of how light interacts with matter. Fundamental research has the potential for many applications because of how fundamental it is. In illustrating all of this to you, I'm explaining to you the process of problem solving, of separating a large-scale problem into its components so that you can meticulously problem solve, the zooming in onto the fundamental questions that you have to ask so that you can apply the answers back to the original problem. The original problem about 10 years ago was actually, when I do this, whatever it was, why do all these vortices disappear? And answering that question led to more questions. Well, what happens if I map this to the arcane plane? What are those structures? What's actually happening around a vortex? What is a speckle field anyway? What is light really? How does it interact with matter? And so you form a body of work. And in the past year, I've worked as a researcher at the Laboratory of Dynamic Imaging, where I have experienced firsthand the rigor of medical research. I realize that there is a quality in a scientist that transcends the field in which one works, and that is the meticulousness in problem solving. This job has allowed me to flesh out those skills, and I look forward to being able to continue my own work in field theory with the assistance of a fellowship, having concluded my scientific adolescence and having entered into scientific maturity. I feel very strongly that there are many people to thank, if you would indulge me for a little bit longer. The time over which I undertook my doctorate was a time of great adversity for me personally, including but not limited to the harrowing loss of my second baby 3 years ago. This prompted a period of mental and physical recovery that is not generally validated. Tension breaking. I want to thank especially my supervisors and Michael Morgan. So my supervisors, David Pagner, who could not be here today, Michael Morgan and Marcus Kitchen, sorry, the angelic Jean Pettigrew, truly, and the wonderful people at Monash Graduate Education for doing whatever they could do to pave the way for me to do my best work in these difficult circumstances. The message was very clear. I am an individual that is not replaceable, and there is something that I have to offer which is worth nurturing. And I want to applaud the School of Physics and Astronomy for having this attitude towards its students. It is difficult to convey how challenging and isolating it was to do my degree with a young child. And I want to thank the school for bending over backwards for me on many occasions and for never wavering in their confidence in me. But I look forward to a time where having women and children with babies in every stage of academic life is so normal that there is no need to make exceptions. But there is one person that I really want to thank above everybody, and honestly that person is myself, for gathering together the enormous strength that was required to finish my thesis. And it is so enormously validating to be given a prize for that work. It has been years since I asked David Pagner to remove the 4 out of 100 mark in first year computing from my transcript. He said that I should leave it in there because it speaks of a journey, which is far more interesting. And I look forward to continuing the journey. And thank you again for this honor.